So welcome. This is a two-dimensional kinematics problem. So we have an x. We're going to imagine x and y axes. It says a particle starts from the origin. It has an initial velocity of plus 4 meters per second. So we'll have plus 4 meters per second and a constant acceleration of plus 2 meters per second squared along the x-axis, and it has an initial velocity of minus 3 meters per second and a constant acceleration of plus 6 meters per second squared along the y-axis. And it says, well, what is its xy position at t equals 5 seconds? Just a brief observation here. So both in the x direction, both the velocity and the acceleration are in the same direction. So this object is speeding up along the x-axis. In the y-axis, the velocity is downwards, but the acceleration is upwards. So it initially starts moving downwards, but it's slowing down. At some point, it will stop. And at some point it will speed up going upwards. So basically what's going to happen is if I was to plot this out, this would go faster and faster and faster and faster along the x-axis. And if I can draw this, this would go slower and then it would start zooming up. So it would kind of go, if I draw this, it would go like that along the x-axis, and it would just take off along the y-axis, and it would just take off along the x-axis. And if I put these guys together, then I think what you see is you get like that, something like that. And it's saying, okay, at t equals 5 seconds, what's your x and y coordinates? Well, you could be down here, you could be up here, you could be over here. There's really no way of telling. So we just got to work this thing out step by step. And the first thing to realize is that when you're looking for X information, you use X information that you are given. And when you're looking for Y information, you use Y information that you are given. And you do not swap the two. The only thing that can go from one column to the other is time. So here we have X info, and here we have Y info. And I'm going to say, well, for my X info, my VI is equal to plus 4 meters per second. I'm looking over here on my diagram. And my A is equal to plus 2 meters per second squared. And my delta T, my time, is equal to, well, it wanted at 5 seconds. And my position, displacement really. I'm going to get displacement, and because I start at the origin, my displacement is going to equal my position because I'm measuring from 0. So my displacement is what I want to find. So let's make a column of that. And then next to it, I'm going to have to squeeze this in. And then next to it, I have VI is equal to, and this is going to be minus 3 meters per second, and A is going to equal plus 6 meters per second squared, and my time, of course, is going to equal 5 seconds, and I call it delta X even if it's in the y-axis, because delta X in my mind means displacement. If you want to call it delta Y, so there's less chance of confusion, you can call it delta Y. Frankly, I don't use subscripts particularly. I won't, as a rule, say VIX and VIY unless there's a good reason to. By the same token, I won't say AX and AY. I'll just keep my columns distinct. So I'll do a calculation only using this left-hand column. I'll do a calculation only using the right-hand column. And so I'm always trying to avoid mixing these two sets of information together. If I look over here, then the obvious equation is delta x is equal to vi delta t plus 1/2 a delta t squared. So for my x-axis, this is going to be delta x is equal to vi is going to be plus 4 times delta t, which is 5, plus 1/2 times my a, which is plus 2 times 5 squared. I'm squeezing things in. This might not work out too well. So delta x is going to equal, well, actually, let's do it up here. Let's do it as along horizontally. So that's going to be plus 20. And then this is going to be plus. And this is going to be 1/2 times 2 is 1. 1 times 5 is 25. So that's plus 25. So this equals plus 45 meters. And then for my y-axis, and now I'm looking at the right-hand column here, I say, well, same equation, delta x is equal to, and it's going to be vi, which is minus 3, times t, which is 5, plus 1/2 times a is plus 6, times 5 squared, which equals, well, that's going to be minus 15, plus, and this is going to be 3 times 25, which is 75. Let me be a bit careful here. Plus 75. So that means that delta x is going to equal minus 59 plus 75 is plus 60 meters. So my x and y coordinate is going to be, for my x-axis, plus 45 meters, and for my y-axis, plus 60 meters. Okay, and we're somewhere up here somewhere. So there's nothing wrong with calling this delta y, and there's nothing wrong with calling this vix and viy and ax and ay. Delta t is delta t. You can add subscripts to help you distinguish between these two columns, but I tend to use the fact that I'm only going to have an equation with x stuff in, or I'm only going to have an equation with y stuff in. When I look to the side, I want plus 45 plus 60. So there's my answer. And if you think about it, it's really two one-dimensional problems. You know, we really only doing a one-dimensional x-axis problem and a one-dimensional y-axis problem. That's not always the case. But for today, for this problem, there we have it.